Hello. Thank you for coming. So today I'm going to talk to you about Swift's encoder and decoder protocols. So you're probably familiar with these to some extent. They've been really baked into all of these server-side frameworks because they give us a really nice way of converting between our Swift types and JSON or any other formats and going back and forth. And so today we're going to sort of dive a little deeper into what's going on inside these protocols, as well as the internals of the types that implement them. So let's just start off by defining encoding. So in this context, encoding is taking a Swift type, putting it into encoder, and getting out some external representation. So the input could be something really simple, like an integer, or it could be like some really complex instance of a subclass. And the output could be something like JSON or XML, or really anything that has a defined structure that you can construct programmatically. So a concrete example of this in Swift is the JSON encoder. So say I have this struct for a point that has x and y values. I could start off with an instance of that point, put it into the encoder, and I get out this JSON string that corresponds to the point. So when I talk about encoding throughout this talk, I want you to think about putting values into an encoder. We are putting the Swift type in and getting something else out. So decoding is pretty much the opposite of encoding. We start off on the right with our external representation, which could be, again, JSON or XML or anything else. We put it into the decoder, and out comes a Swift type. So a concrete example, again, would be the JSON decoder. We start off with that same string, and we get out the point. So I want you to think of decoding like taking a Swift type out of a box, because we put in the string, and out comes a point. So Swift 4 introduced a standardized approach to encoding and decoding data, as well as for writing encoders and decoders that do it. And what I really like about it is that it's totally agnostic to the format you're actually encoding to or decoding from. And so today we're going to talk about how it actually works and how all these pieces fit together. But first, why would you care? Well, as I mentioned, you probably are relying on it already if you're writing any kind of server-side Swift code. And more knowledge of how exactly these encoders and decoders work will make it easier for you to customize how your types get encoded and decoded. If you want to do things like omit a property or rename it, you want to flatten some nested struct that's inside your type or anything like that, knowing about how this works will give you the ability to do that. And then if you even want to take it a step further, knowing this will make it easier for you to write your own encoder or decoder. So I had to do this pretty recently. I've been working on a new MongoDB driver for Swift, and so we wanted to have a BSON encoder that would allow us to take Swift types to MongoDB documents, and a BSON decoder that would let you do the reverse. So I've gotten pretty deep into how all this stuff works, and I'm going to share that with you now. So we'll start off by talking about the sort of public API, what you see as a user of an encoder or a decoder, and what the requirements on the protocols are. And then we'll talk a little bit about the internals of encoders and decoders, and the kind of things you need to think about if you're going to write one. Finally, I'll talk about some sort of limitations that this protocol, or that this whole system has, and ways that it could be alleviated in the future. OK, so let's dive into the public API. So one key component of it is the protocol Encodable, which you've probably seen before. It has just one method that writes the value into an encoder. So an encodable type knows how to store itself in an encoder. And some important things to note about this protocol. You get automatic conformance if all your properties are encodable already, which is often the case. Types can provide custom implementations if they want, and in fact, they have to do so if their properties are not all encodable. And as I mentioned before, it's format agnostic. So you write this one time, and it'll work with any encoder out there that conforms to the encoder protocol, which is really cool because you don't have to know what they look like. You don't have to know anything about the format. It just works. And the reverse of this is the decodable protocol, which allows you to initialize the value from a decoder. So basically, the type is reading values out of the decoder and taking them out. So pretty similarly to encoders, or encodable, you get automatic conformance if all your properties are decodable. But types can provide custom implementations if they want to. And you write it one time, and it'll work with any decoder out there. So you'll often hear people say Codable, because it's really common that you want to be able to go both directions with your types, and you make them both encodable and decodable. So a lot of types have built-in Codable support already, which makes it really easy for you to make most of your structs just codable out of the box. So all the number types, bools, strings, and then there's sort of all these special cases where if the values they contain are encodable or decodable, then the type is too encodable or decodable. So like an array, if all the elements are encodable, the array is encodable. The same is true if all the elements are decodable, then the array becomes decodable. So we get that behavior as well with sets and dictionaries and optionals if the wrapped value is encodable or decodable. And then some of the common foundation types, especially those that you might want to be using with, say, a JSON encoder or decoder, also have built-in support for a codable. So if you want to make a type codable, here's how you do it. So say I have this simple struct for a cat. It just has a name and a color. All I have to do is just add that it's codable. Since both of these properties are types that have built-in support, the compiler will generate those encode and decode methods for me for free. So that's all we have to do. And so if we want to use this struct with an encoder and decoder, we would do something like this. So let's create a cat. We'll make one for my cat, Roscoe. And we'll encode him using a JSON encoder. So the public API to a JSON encoder looks pretty much like this. We just have this one method that takes an encodable value and gives us data, and that data is UTF-8 encoded. And so the flow of information is kind of like this. So if we wanted to use this encoder with Roscoe, we would create a new encoder and pass in Roscoe. And then if we want to confirm that we got what we expected here, we could create a string using that data and tell the constructor that it's UTF-8 and print it out. And sure enough, it looks like what we expect. So one thing that's kind of confusing is that this API doesn't match the encoder protocol, right? So this is the JSON encoder API, but this is the method, or the encodable protocol. But this is the method you actually have to implement. But we're not calling like value, like Roscoe.encode to JSON encoder. So what's going on here? So basically, the way that the JSON encoder is designed, it points to a private class that actually implements the encoder protocol. And the same is true for property list encoder, which is also one of the built-in Swift encoders. So the idea there is that we're able to sort of separate different parts of the API based on what the user needs to be able to do when. So the top level, it's not dictated by any protocol, so it can be really specific to whatever format you're encoding to or decoding from. And often it will allow you to set top-level options. So for example, JSON encoder has a date encoding strategy because you might want to encode a date as a double, or you might want to do all these other different kind of things. And it has a really simple API that's all the user really needs to think about when they're using a JSON encoder. On the other hand, this encoder actually implements the encoder protocol. So it does all the work of encoding, and it has a much more complex API, which we'll talk about in a little bit. But this allows us to sort of cleanly separate what the user needs to think about when. So using a decoder is quite similar. So if you look at the API here, we again have this one method. This time we have to supply the type that we want to decode to and the data we're decoding from, and we get the type out. So we're basically doing that sort of reverse of the JSON encoder method. And the data is going in this direction this time. So if we were to use this with my example from before, so this is the data we got out from the encoder. We'll round trip it now. So we can pass into the decoder and tell it that we want to get a cat out. And then when we print it out, sure enough, it's that original cat that we started out with. And again, the API here doesn't match the decodable protocol because the decoder is architectured in the same way with this private class that actually does the work and implements the protocol. OK, so now let's talk about what these protocols actually require and what they look like. So basically, an encoder's main job is to provide you containers to encode things into, which are kind of like views into its storage that types can write themselves into. So there's 3 different container types. The first is a single value container. So that's for a type where we only need to store one value, like an integer, for example. The next type is an unkeyed container for a sequence of values. So you can think of that like sort of a special array. And then the final type, and the most common, is a keyed container for storing key value pairs. So basically like a dictionary. And in code, this gets translated pretty directly into these 3 methods on the encoder protocol. So there are some other requirements of the protocol, but they're mostly like bookkeeping related or special cases. So I'm going to focus on these for now. So each of those container types supports storing 3 different types of values. One of them is sort of like a base case, which is just encoding nil. The next one is a primitive type. So that could be like a bool, a string, a double, a float, basically things where we can't go any lower and like deconstruct them into more parts. And the final would be like a recursive case where we're using an encodable type that probably is like storing other things in it, and we're going to have to go down a level. So the methods to encode these to containers show up on the protocols like this. So we have the single value container with these 3 different methods. Although I'll note that the second method is not actually just one method. So I've left this in what's called GYB, or generate your boilerplate format, which is something that like the people developing Swift use when they need to do something really boilerplatey. So basically, think of this as like a for loop that's adding an encode method for all of those primitive types I listed before. So really, this protocol has something like 10 or 12 methods required. And then unkeyed encoding container actually looks exactly the same as single value encoding container. The only difference here is that you should only call one of these methods one time for a single value container, because it's a single value. In the unkeyed case, it's OK to call them many times, because you're storing a sequence of values. And then finally, we have the keyed encoding container protocol, which looks pretty similar, but this time we need to provide keys when we encode values to say what we're actually storing the value under. And the protocol has this associated type, which is a coding key. So let's talk about coding keys for a bit. We see that show up on the encoder protocol. When you request a keyed container, you need to tell it the key type you're using. And then in the keyed encoding container protocol, we actually have that associated type. So coding key is a protocol that looks like this. It should have initializers that can potentially fail from string and int. And then it should definitely have a string representation. And it might have an int representation. And you get conformance for free if you use an enum, which I guess kind of makes sense because you can just take whatever the name of the case is and make that a string. So it's convention. Most people will use enums when they're doing coding keys, but they don't necessarily have to be one. So there's also the possibility that you could have nested containers. So both unkeyed and keyed containers support nested unkeyed and nested keyed containers. Just something you would use in that like recursive case where you're storing a type inside of another type and you need to go down a level. And we see these show up on the protocols pretty much like this. So in addition to those encode methods, we have these nested container methods that create nested keyed and nested unkeyed containers. So how would you actually use these containers? Let's go back to our cat example. This time we will use my other cat, because I have to be fair, Chester. So we'll create a cat for him. And then we want to encode him using the encoder. So looking at the structure of Chester, probably makes sense that the kind of container we'd want to use is a keyed container, because we have 2 labeled properties. So we would create a keyed container. And the keys would be name and color, and the values would be Chester and Tan. But how would you translate that into code? This is one of those cases where the compiler generates it for you, but let's go through what the code would look like anyway. So we need to define those coding keys. In this case, we just have these 2 keys, name and color, pretty simple. And then the encode method looks something like this. So we create a container keyed by our specific coding keys, and then we encode the properties on their specific keys. So notice that it's really nice using an enum rather than just like strings here, because the compiler will be able to tell if I like make a typo and that sort of thing. So it's a lot more safe. But of course, we don't actually have to write this. It's compiler generated. But what if we don't want that default behavior and we want to do something different? Like, say, for example, I don't know, I'm going to send this cat to some API that requires the cat's name is called first name. But I don't want to change my type internally. I still want to call it name there. So I can do that by just overriding the coding keys. So I can set name to have a like raw value of first name. And then when I encode the properties, it will still use the default encode method, but we'll use these key names instead. So then I'll get this sort of structure over here, with first name and color. So you can use this to rename your keys. I could have also renamed color if I wanted, but I can also just keep it as is. Another case, you might want to omit a key. And so if I want to leave out color. So I could do that by just not including color in my coding keys enum. And again, I don't actually need to write the encode method. The compiler will just look at my coding keys and be like, OK, there's only one for name. That's all we'll encode. So that's another way you can sort of customize what happens. And then, of course, you can actually customize the encode method itself. So say I want to lowercase the cat name before I send it. So in that case, I could write the encode method and modify the name when I write it to the container. And I could do all kinds of crazy complex things in here. But here's a simple example of how you might do that. So I could even be creating nested containers and putting more things in them if I wanted to. So let's make this example a little more complicated. We'll introduce a cat owner type, which has name and an array of cats. So you can probably see where this is going. So I have my cats for Chester and Roscoe, and then I have a cat owner for me. So if I wanted to encode myself, how would I do that? Well, cat owner is another case where we would probably want to use a keyed container, right? Because we have these two named properties. So that would look something like this. So we put the name in, that's easy, but now we need to figure out what to do with cats. Because this is an array, so we can't just stick it all in there. So this is a case we're going to need to use one of those nested containers. So we'll use a nested unkeyed container here to represent cats. And then in each of those spots, we're going to need to put a cat. Again, a cat isn't just a single value, so we're going to need more nested containers. So this time, we'll create two nested keyed containers to put Chester and Roscoe in. So if we were to write out the code for this, even though we will get it for free from the compiler, it would look something like this. We would have these coding keys, as before, and then the encode method would look pretty much like this. We create a container with our keys, just like before, and then encode each property. One thing you might be wondering is, how is this one line creating that entire bottom structure of containers, right? I only did one thing, yet somehow we've gotten this far in. So let's look a little more deeply into that. So here's that encode method that I wrote for the cat owner. And so in this last line, when I call encode cats, I'm encoding an array. So this is going to then go, we create this container, and then when we encode the cats, it's going to call the array encode method. And so that array method is encode method is what's going to create this unkeyed container. And then we iterate through the array, and for each of the elements in it, we encode that. So then that's going to go down and call the cat encode method, which will create these nested keyed containers for us. So the encoder is responsible internally for sort of figuring out how to create that nested structure in the correct place when we're going down a level and encoding encodables. Alternatively, we could have written this like this. We could have totally flattened it out and not relied on going down the different methods, because we do have these ways to directly create nested unkeyed containers and nested keyed containers from the top level. So maybe I would do this if for some reason I didn't want to make cat codable, or something like that, and I want to have it all here. But I prefer the first approach because it allows us to sort of cleanly have the code for encoding a particular type with that type, as opposed to being a level above. But sometimes you may need to do this if you need to, make some kind of decision about what to encode or decode based on additional context. But again, that default behavior will be generated by the compiler for us. All we actually needed to do is mark cat owner encodable. But now you have a basis for what that looks like if you ever wanted to customize how something like this gets encoded. So at this point, you might be like, you've been talking about encoding for a long time. Weren't we also talking about decoding? That is true. But I wanted to get fully through sort of the encoder protocol first. And the reason is that these protocols are actually kind of the same. As I said at the beginning, you can think of encoding as putting values in, and decoding as taking values out. But that's really the only difference. Otherwise, this whole structure of nested containers in the storage system is really kind of the same thing. Again, we have these same types of nested containers and these same container types that correspond to the same kinds of values. And they show up in a very similar way on the decoder. And again, each of the container types supports these same 3 types of values. So the protocols look kind of like this. It's quite similar to before, but this time we need to pass in the type that we're trying to get out. The compiler can't figure that out for you, because who knows? It could be any type, right? And the unkeyed container is very similar again, as is the keyed container. Again, we're just passing in the type that we want, and then this time we also need to pass in a key that we're encoding or decoding under. So if we were to decode this, we would use that same kind of container structure as before, but this time it's just a decoding container. But we can look for the values that we want to pull out in the same place that we would expect to encode them to. So if we were to write out the compiler-generated stuff for this, the coding keys are exactly the same as before, and you'll notice the init even looks the same. I realize now that these lines should be assigning those last 2 lines to the properties. So it should be self.name is that one, and self.color is that one. But you get the idea. You pull out your particular properties, you request them under the keys that you stored them under, and then you set them on yourself. But we don't need to write that. It's generated by the compiler. But we can customize it in much the same way we are able to customize encoding if we want to. So here's some takeaways from this public layer. Types opt into conforming to encodable and decodable by marking themselves as such and potentially implementing the methods if they need to. A lot of types get conformance for free, but they can customize when they need to. Most of the public encoder types, or at least those built into Swift, don't actually implement the protocols that go along with the type that they are, but instead rely on some private implementation to do so. And both encoders and decoders use really similar container-based APIs for reading from and writing to storage. So overall, they're very similar. So now let's kind of go down a layer and talk about what's going on underneath the hood inside encoders and decoders. So as I mentioned, the architecture is usually that you have this private implementation of the encoder-decoder. And then usually that also points to some kind of storage, because you need a place to keep values while you're in the middle of doing things. So that storage could potentially be within your encoder-decoder itself. But this is the pattern that Apple has followed and that I have followed. So let's talk a little bit more about storage in general. Like, what do I mean by that? Basically, what I mean is, how do I store values while I'm still in the middle of encoding or decoding? So there's not one particular right answer to this. It's sort of really dependent on what format you're using. But I'll give you some examples. So for JSON encoder and decoder, the way that Apple actually converts things to JSON and parses JSON is by using JSON serialization. And that will work with a bunch of the NS types, like NS array, NS string, and that kind of thing. So as soon as you put a value into a JSON encoder, it gets converted to an NS whatever, the corresponding one. And it stays that way until the very end, when the whole thing gets passed to JSON serialization. Similarly, going in the other direction, we immediately parse the data into this sort of nested thing made up of NS types, and then values get pulled out of that as we decode. And the property list encoder and decoder really do exactly the same thing, because property list serialization supports the same kind of NS types that JSON does. For a slightly different example, we can talk about my BSON encoder and decoder a bit. So in the BSON library, we have a BSON value protocol, which indicates that a type is a BSON value and can be put on a document or stored in a document. So in our case, since the BSON encoder is converting Swift types to documents, we immediately convert your value to something that will later be able to be stuck directly onto a MongoDB document. So there's not a right answer to this, and all of these are admittedly very much based on a sort of key value type structure, like a document-based thing. So if you were to write some sort of very different format encoder-decoder, this might not apply. Another thing you need to sort of think about is how you track where you are in this whole maze of nested containers. How do you make sure you're writing to the right one and things are being put in the right place and that sort of thing? So the only real solution I've seen to this so far is by using kind of a stack. So when you go down a level and you need to create a nested container, you put that on top of the stack. when you're fully done encoding everything, you pop it off, and then you put it inside like whatever the container above it is. So there may be other ways to do this again. I'm not, but I don't know what those are, so let me know if you know any. But this is a kind of good way to track where you are in the whole process and make sure things get put in the right places. So here's some other things that didn't really warrant talking about in a whole slide, but are important to note if you are going to write an encoder decoder. Often the single value container types are just implemented as extensions of the private encoder type. And the reason for that is that the requirements of encoder and single value encoding container don't really conflict. You'd have to sort of look into the JSON code a bit more to see why. But point is, you don't necessarily have to write a separate type for every single protocol that is required by this ecosystem. Additionally, I mentioned before, you have to make sure that only one value gets encoded to a single value encoding container. That's not something the protocol enforces for you. You just have to do that. So you can kind of find all these special edge cases if you go in the source code for an existing encoder decoder and just search for precondition. But that's another thing to consider. And there are a lot of bookkeeping requirements that you need to maintain throughout. These are sort of just annoying, pushing things onto arrays and taking them off and that kind of thing. So I didn't cover them today. But that allows you to sort of track where you are in the process of encoding, also give good error messages and that sort of thing when something goes wrong. And there's also these super encoder and super decoder requirements that are for use with classes. I didn't cover that today, but you can usually sort of build on the existing types you've built for the other requirements to implement that. So there are some limitations to how this whole thing is designed. For one, there's a lot of boilerplate required. If you remember that place where I just left in the for loops, iterating through all the types, you can imagine that implementing all of those methods for the primitives on every single container gets really kind of boring and ends up requiring a lot of copy pasting, basically. So that can be frustrating from the perspective of someone writing encoder decoder. However, it means that it saves your users from writing a ton of boilerplate, like all that stuff we went through before with a compiler-generated code. So it's a bit of a trade-off. Depending on the design of your encoder decoder, you may end up duplicating a lot of stuff from JSON encoder decoder. Since they're sort of the example we're all working from as we write these, you naturally kind of want to do something similar. However, the only thing that's public about the JSON encoder, the JSON decoder, is that top level one. So it's not like you can reuse their types that are within there. So yeah, it's in my BSON encoder, there's a lot of stuff that's mostly just copy pasted. And slightly changed. And so it's been proposed, maybe you should, maybe all those types should be included in the standard library, but it's kind of weird, you wouldn't necessarily want those to be public types, right? Because they're not meant to be used, they're just meant to be used by a type that is public. So it's not really clear, how that fits in, API-wise. Another thing, you can't extend types to become codable because it's a required initializer. Or to become decodable. So that can be frustrating. For example, when I was writing the BSON decoder, we were using NS regular expression to represent BSON regular expressions. But NS regular expression is not decodable. So basically, I hit a roadblock because I couldn't actually make all of my BSON value types decodable. So the workaround for that ended up being making my own type that points to an NS regular expression and is decodable. But some might argue that it shouldn't be possible to do that anyway because you don't really know how that type might change in the future. Maybe the person who developed it will eventually make it decodable and then that implementation would conflict with yours or that kind of thing. Okay, so my main takeaways for you are that the API makes conforming decodable and using it really trivial in many cases, but it also allows you to customize things a lot when you want to. It also makes it possible to write encoders and decoders that have no idea what the types using them look like, and it makes it possible for types to use encoders and decoders without caring about the actual format, the external representation that's being used. And finally, if you investigate the standard library source code and write your own encoder and decoder, you'll find a lot of hidden sort of requirements that are not really clearly spelled out by the protocols, but are required to make things work correctly. That's all I've got. I'm happy to take any questions.